everyone, I'm Joe. Welcome to my channel again. And today, let's continue to talk about the modular combinational circuit. Today's topic is multiplexer and the demultiplexer. Multiplexer, sometimes is also called data selector, is defined as a circuit that directs one of several digital signals to a single output, depending on the states of the selected input. So basically, for the multiplexer, we should have multiple input, and we have only one output. Here the input and output, I mean data input and data output, and we also have some select input. This select input works like a controlled switch. You can look here. Based on the value of A here, we can determine where the switch located. Then the corresponding input data will be passed to the output. So that's why it's called data selector. To name a multiplexer, we can call it n to 1 mux. N is the number of input, 1 is the number of output. You can also call it 1 of n multiplexer. Okay. So 2 to 1 mux is the simplest mux, and we have 4 to 1, 8 to 1, 16 to 1 mux too. So for the 4 to 1 mux, because we are selecting among 4 data input, so we need at least 2 select input. So the number of data select input and the number of data input has the relation like n to the power of n, right? And this is actually the logic circuit using the logic gates for the 4 to 1 mux. If we write down the truth table for the 4 to 1 mux, it should look like that. So the input is the select input, and so we usually don't show the data input here, because we just need to figure out the relation between the output and the input. So we don't have to show every possible combination here for the data. So we have y. So if this is 0, 0, we know that the data d0 will be passed through y. So y will equal to d0. Whatever value d0 is, y should equal to that. And the 0, 1, d1, 1, 0, d2, 1, 1, d3. And here is the trick how we can write the Boolean expression for y, even though we don't know, we don't show all the possible combinations. So y would equal to, think about this, y would equal to d0 when s1 is 0 and s0 is 0. Right? You can check if s1 is 0, s0 is 0, then y should equal to d0. And y will equal to d1 when s1 equal to 0, s0 equal to 1. Similarly, you can write y equal to d2 when s1 is 1 and s0 is 0. Finally, if s1 is 1, s0 is 1, y should equal to d3. So actually we can write the Boolean function of the output of a multiplexer. This is an example of an 8 to 1 mux with an enable input. If you remember what is an enable input for decoder, so same thing here. So enable just the input to turn on and off the function of this modular circuit. Okay, and just like usual, in most cases the enable is active no. So basically, if the enable bar equal to 0, the mux will work. Basically, you can also say if this is equal to 1, then it doesn't matter what select input or data input you have here, the y always equal to 1 and the y bar always equal to 0. Okay, it's just a fixed value. You have to turn this to 0 for it to work. Then it can do the multiplex. And yeah, here I don't want to show the truth table again. You can figure out, right? For 8 data input, we need 3 selected input. But what I want to try again is how to write the output Boolean function. So y should in this time should equal to what? S2 bar, S1 bar, S0 bar. When this happens, it should equal to D0. S2 bar, S1 bar, S0, D1. S2 bar, S1, S0 bar, D2. S2 bar, S1, S0 should be D3, or S2, S1 bar, S0 bar, D4, or S2, S1 bar prime, sorry, not bar, S0 by D5, then S2, S1, S0 prime, D6, S2, S1, S0, D7. So this is the output Boolean equations. Okay, and just like decoder, we can use the enable input to cascade two multiplexer together to make a bigger multiplexer. Like in this case, we have two 8 to 1 marks here, and we can cascade it into a 16 to 1 multiplex. Okay. Yeah, because for the 16 to 1 marks, we need 4 select input. So here we have S2, S1, S0, 3 select input for each of them. So we collect them together. Then we use the enables as another one. But all we have to do is put a NOT gate here. So at any time, only one of these 2 marks will work. Okay, so that separates the 8 input. Totally, we have 16 inputs here. Okay. You can try to do your own analysis to see how this works, but it has the same truth table as the 16 to 1 marks. We can also use multiple 4 to 1 multiplexers to realize 16 to 1 marks. Okay, a similar idea as how we expand the decoders. So we can use 5 4 to 1 marks to realize 1 16 to 1 marks. So the idea is that we use an extra marks to mark the output of the other 4 marks. Got the idea? So let's check this circuit here. So S3, S2, S1, S0 is the 4 selected input, which is needed for 16 to 1 marks, right? So if we check if S3, S2 is 0, which means the marks 0 will be selected, will be marked to the output, right? And S1, S0 will determine which input of marks 0 be sent to its output. Finally, it's to the real output, the final output. So if it's 0, 0, which means input 0, we're showing it this y out here. Let's call it y out. If it's 0, 0, 0, 1, it still marks 0. So in 1, 0, 0, 1, 0, still marks 0. In 2, 0, 0, 1, 1, still 0. In 3. But after that, if S3, S2 become 0, 1, then max 1 will be, the output of max 1 will be maxed to y out. And if S1, S0 is 0, 0, we will get in 4. And so on. Finally, we can get 1, 1, 1, 1. Then in this case, max 3 the output of max3 will be max2 y out, and it's because s1 s0 is 1 1. Okay, so which means the data input 3 will be maxed to its output here, which corresponding to the total input 15. Okay, actually we don't need that. Applications of mux. The first application is that we can use the mux to realize specific Boolean function, just like the one shows here. This is a 4-variable function in min-term list form, right? To use mux to realize that, we need to first set the select input to equal to the variables. So basically the S3, S2, S0, S1, S0, we make them equal to A, B, C, D. Following the same sequence here. So A is the MSB corresponding to S3, D is the LSB corresponding to S0. Okay, then because we know how to write the output function for the mux, which equal to A prime, B prime, C prime, D prime, E0, or A prime, B prime, C prime, D, E1, or we can skip the middle one. So the last one would be A, B, C, D, E15. So actually we can tell that this select input now form the min terms of this function. So we can rewrite this as M0, E0, M1, E1 until M15, E15. So all we have to do is configure those data input, right? If we can fix the value for data input, then we can pick out the terms we want to realize that function. So in this case, what we need to do is for E1, E4, E9, and E15, we collect them together and fix them to the power supply, which is logic high, right? Then the M1, M4, M9, and M15 in this expression will be retained. For the others, we also don't forget to configure them, because we have to make those terms to be 0, right? So we need to fix those data input to ground, which is logic 0. That's how we realize the function. And there's another way to do this using an 8-to-1 mux. So I don't know why I put this here. Anyway, let's ignore this for now. So here what we do is we also using 3 variables here as the select input, S2, S1, S0. Okay. Or I just do ABC. Maybe this is a little easier, but technically we can do either way. Okay. So we remember. Do you remember the output function for 8-to-1 mux? So it's equal to A prime, B prime, C prime, I0, or A prime, B prime, C, I1, or A prime, B, C prime, I2, or A prime, B, C, I3, or A, B prime, C prime, I4, or A, B prime, C, I5, or A, B, C prime, I6, finally A, B, C, I7, right? That's the output function for this multiplexer. So we can tell how to, they probably still how to form the min terms as shown here, right? So we got 3 variables here. We are missing the other variable d. So basically we can configure I, the data input, to equal to the value of d or d prime. So for the first term, so m1, how to realize m1? Actually, all we have to do is set this to d, right? Then we got m1. For m4, which one we should use? Actually, we can use this one here, right? I2. If we set I2 to be d prime, we got m4. For m9, which one? We can use I4, right? If we set I4 to d, we got m9. The last one, 15. So we just need to set I7 to d. Now we got clear. So m1, we collect it to d, okay, the variable d, and m4, for I2 collect to d prime, and I4 collect to d, I7 collect to d. Then we just collect all the other unused input to ground, not equal 0. We can also realize this function. The second application of mux, which is also the most common usage of mux, we use it to build up the switching systems. For example, say today we have, in your home, you have a home theater system, right? And you have the audio amplifier and the speaker, everything, and you can connect it to your iPod, computer, or satellite, and TV cable. Okay, but sometimes you need different music sources, right? Then you need a mux to select among those different sources. So the application of this is quite straightforward. Depending on how many devices you have, choose the right mux. Right? You just need the switches to configure the select input. Then you can control which music source to use. Okay, so this is very simple. Another very common application of mux is that we can combine multiple 1-bit mux to make a bus mux. A bus is a group of wires. It's very commonly seen in the computer system. Like you hear those terms like address bus, data bus, right? When we talk about bus, we talk a group of wires, multiple bits. They can send multiple bits of data or address. Okay, and so we can build a mux that can select among different buses. So this is an example. We use 4221 mux to realize a 4-bit bus mux, a 221 bus mux. So here you can see that this select input for the 4221 mux is collected together. So which means they always select the same data from each mux there. Okay, so if a equal to 0, it will select so x0 to z0, x1 to z1, x2 to z2, x3 to z3. So you can think the bus. So the bus x is passed through bus z. A equal to 1, the bus y will be passed to bus z. Okay, so that's how it works. And this is an example for 4214 4-bit multiplexer. So each D and Y you see here, they are 4 bits. So this slash means this is a bus, not a single wire. So it's a 4-bit. And when S1, S0 equal to 0, 0, we know that D0 will be marked to the output. So the 4-bit in D0 will be marked. If S1, S0 equal to 0, 1, the 4-bit in D1 will be marked to the output. For the other two, similar case. Okay, after talking about marks, now let's talk about demarks. Just like decoder and the encoder, demarks is the opposite of marks. So we know that marks is select among different input and send it to the output. So demarks is sending the demarks has multiple output but one data input. Then it will select among the different output to send the input data. Okay, the opposite. And physically, a demultiplexer is the same as a decoder with enable input. One example you can see is here. We can configure the 4 to 16 decoder as a 1 to 16 demarks. So basically what we do is we change the for data input for the decoder as the select input. Then we use one of the enable input as data input. So in this case, the data is not really being passed to the output, but the output will basically it's what happens is the output following the value of the input. So there's no physical path inside, but to our eyes we see the signal change, the signal synchronized each other. So it looks like the signal is passed through. We realize the function though. Okay, so for example, if S3, S2, S1, S0 in this case equal to 1, 1, 1, 1, okay? So we know that the D15 will be active, right? So it's equal to 0. But this will happen only when the data in equal to 0, right? Because it's an enable input. It has to be active for the decoder to work. So the data in, if data in is 0, then this will happen. However, if data in is not 0, the decoder doesn't work at all, so the output will not be activated. It will be 1. So it looks like the D15 in this case, with this input here, the D15 is following the data in. It looks like the data is passed through. Okay, so that's how the demarks works. It has the same circuit as decoder. Okay, so the application for demarks is also the opposite of marks. Before we talk about the marks, can select among different sources, right? Now the demarks will be used when you want to send the data to different destination. Like in the computer, for the computer, we want to use different peripheries like printer, fax machine, right? Or I'm not sure. So it's a pen plotter here. Okay. So anyway, if you have multiple output, you can use the demarks to determine where the data you want to send to. Okay. That's it. Okay, finally, thank you for watching this video. If you think this helpful, please like, share, and subscribe. I will see you next time.